Okay, today we are going to see the pipelining and hazards. I am Dr. Naveen Sundar, Assistant Professor, Department of CSE. So, what is pipelining? I want to take a case study of building a car when it is unpipelined. Okay, so series of jobs, that is, we are going to manufacture a car. Okay, so it takes 24 hours to manufacture a car. When it is a sequential execution, how we are going to differentiate with the pipelining. So when you take, if it is an unpipelined, it takes 24 hours for manufacturing a single car, and after that we are going for the next 24 hours for the next car to manufacture. So when we calculate the throughput, okay, so it takes one car per 24 hours. Okay, so when we are going for parallelism, how we are going to improve the performance. So when you see the pipelining concept, we are breaking the job into smaller stages. That is the same concept we are going to use for program execution. So consider here A, B, C. We are manufacturing a car. We are splitting it into smaller stages. When you see A, that means manufacturing the engine alone, and then manufacturing the body part, that is the B, and then we are going for painting, that is C, right? So here in pipelining we are splitting the job into smaller stages. Initially we have seen all the three parts we are making 24 hours. Okay, so this take alone only 8 hours, and then for body part similarly again 8 hours, and painting again 8 hours. So it takes 24 hours, but we are splitting the job, okay, into smaller stages. So once the engine part get over, okay, so that person who is allotted for it will be free, so we can give and manufacturing the engine part for the second. Okay, so that's why we are telling it in the second row A, we are going for engine manufacturing at point A. Similarly, once the body parts of the first car is get over, okay, we are just allotting for B in the second, for the second car. And similarly for C, when we do such things, okay, so the throughput now we are taking it is like per car only 8 hours. Okay, so 3 cars can be done at a parallelism. Okay, so but initially we can do only one car because it is a sequential manner. After finishing the one particular car manufacturing time, then only we are going for the next car for manufacturing. But when we split into jobs, once the engine person, okay, manufacturing person is free, we can allot the second car for manufacturing the engine. So we can reduce the time and we can improve the performance. Now we are seeing the same concept in an instruction execution. When it is unpipelined, okay, so we have different stages like fetching the instruction and decoding the instruction, and finally we have to go for executing the instruction. When we are not splitting into jobs, that is sequential, after finishing the instruction 1 to get executed, then we are going for the next instruction, right? So this is how we are going for unpipelined. Okay, but when we go for the pipeline concept, here you can see the same concept how we are manufacturing the car. Here A, B, C, we are breaking the job into smaller stages. That is, fetching will be done at the clock cycle 1, and then decoding at the clock cycle 2, and execution. Okay, so that stage will be in the clock cycle 3. Okay, so once the fetch cycle get over at the clock cycle 1, it will be free. Okay, so we are just fetching the second instruction. Okay, at the clock cycle 1 we are fetching the instruction 1, but at the clock cycle 2 we are fetching the second instruction. At the same time we are doing parallelly, we are going for decoding of the first instruction, right? So this is the pipelining concept. Once that stage is free, we are allotting the other instruction to follow the process. Okay, at the clock cycle 3 we may see 3 instruction. Okay, it is in parallel. That is, first instruction is doing execution, the second instruction is doing decode, and third instruction is doing the execution. So this is how we are going to reduce the number of clock cycles by improving performance in pipeline. Okay, at the clock cycle 3. So now when we compare the throughput, we can see in unpipelined. Okay, so that is the clock speed. Okay, so that is 1 by 3 ns, that is we are going for 3 number, that means 333 megahertz. Okay, so this is how we are having in unpipelined. But when we come for pipelining, okay, so it is increased to 1 gigahertz. Okay, so we are improving the speed, clock speed, when we go for the pipelining, because three stages doing serially in unpipelined, but only one, okay, at the time. So we are improving the performance. So now we will see about the hazards. So till now we have seen about how we have improved the execution of in section performance by means of a pipelining. But there are some hazards will occur. Okay, sometimes when we go for pipelining, we will see three types of hazards. That is the structural hazard. Okay, that is the different intersection in different stages conflicting for the same resource. Sometimes the resource conflict occurs due to the memory or due to the registers what we are going to use, that we will see in the coming slides. And data hazard, okay, so an instruction cannot continue because it needs a value that has not yet been generated by an earlier instruction. Sometimes this will occur. Okay, so that is the data hazard that will occur due to not providing the data correctly. And control hazard, that is it can fetch, cannot continue because it does not know the outcome of an earlier branch. Sometimes the branch instruction occurs. Okay, so that is the time the program counter value will be incremented as normally by the sequential execution. But when the branch instruction occurs, we have to increment the program counter value according to it. Okay, so we have to decide whether branch instruction to be taken or not, so that takes time how we can resolve the issue, right? So these are the types of hazards we are going to see, and how we are going to solve the data hazard by means of forwarding and bypassing, and how the control hazard by branch delay slot, and structural hazard again we will go for some other technique how to resolve it. Okay, so first we will see about how the hazard occurs, and then we will see how these hazards can be removed, okay, for improving the better performance in pipelining. So first structural hazard, okay, when I see the A5 stage pipelining, okay, so initially at the clock cycle 1 we will fetch the instruction, okay, so and the next is the decode part, okay, and also we will fetch all the operands that is required, and at the clock cycle 3 we will go for the execution that is done by the ALU, and at the clock cycle 4 we will go for storing the data into the memory, and clock cycle 5 again store back the result into the registers according to the instruction what we are going to give, right? So these are the five stage pipeline. Okay, so here you can see from the diagram, you can see the memory we are using at clock cycle 1 and also at clock cycle 4, and also similarly we are using the register at the clock cycle 2 and at the clock cycle 5. So easily you can understand when we go for pipelining, surely there will be some conflict occurs in using the resources like memory and registers. Let us see how it got conflicts. So at instruction 1, okay, so we are storing the result at the clock cycle 4, okay, so that is the data memory, okay, we are going to store the result into it. Okay, so why we are denoting at the instruction 1 at clock cycle CC1 is IM and CC4 is DM, means we are going to fetch the instruction from the memory, that is CC1, and storing the data into the memory. Okay, so that's why we are given it as IM and DM respectively, right? So now when we see at the instruction 4, okay, up to 3 instruction getting execution, then no problem for no conflict occurs. But when you see at the instruction 4 to get execute, that is the time we are fetching the instruction from memory. At the same time, at the clock cycle 4, the instruction 1, we are storing the result, storing the data into the memory. So that is a memory conflict occurs. Okay, so this is called a hazard. Okay, so we can't proceed at the in section 4 to fetch. So what we are doing is we are just sending the bubble. Okay, so bubble means we are not doing any useful information during that particular clock cycle. Okay, so when we go for DM, okay, so that is the in section 2, Okay, so that is the time again we are storing the result into the clock cycle 5. Okay, so clock cycle 5, that is the time again. Okay, so the conflict occurs, the instruction 4 cannot be done in that particular time, so again we are going for bubble, right? So similarly, at clock cycle 6, if we try again, the instruction 3 get conflicted, we can't fetch the instruction at the clock cycle 6. Okay, so this is how the instruction 4 get delayed. Okay, so the 3 instruction we are making a pipelining good. Okay, and the next 3 we are making a bubble. Okay, we can't proceed further. Okay, so that is how we are going for, and finally when we go for at the clock cycle 7, we can resolve the issues. Okay, so we can clearly say how the performance is degraded. Okay, so we can say the 0.5, so first 3 instruction is get pipeline, and the next 3 instruction it is not yet pipeline. Okay, so this is how the consecutive pipelining concept occurs. 3 instruction we are getting pipeline, and then 3 bubble, and then 3 instruction pipe. This is how the performance, okay, of the pipelining get degraded. So how to resolve this issue? If we provide, okay, for instruction fetch, that is IM, and data to be stored into the memory, that is DM, if you make a separate memory for this, okay, we can resolve the issue, but it will be more costly based upon the architecture. Okay, so they will, to resolve this structural hazard, they will use a separate memory for instruction fetch and to store the result into the memory to resolve this issue. Okay, and the register file access. So now till now we have talked about the memory. Okay, so instruction memory and data memory, and how the conflict occurs and how we resolve the issue. Now we will see about the register file access. How this register file access? As I told you, the register read and write also happening, that results to the conflict in the clock cycle 2 for the instruction 1, and at the clock cycle 5 we are using the register. So how we can resolve the issue? Okay, so what we can do is, at the clock cycle 2 we are making it into two parts. Okay, so at the clock cycle 2 we are making it into two parts. Okay, so that is, one is decoding part will takes place, another one is read. Okay, so that's why we are making at the clock cycle 2, when you see the diagram, okay, the second portion is in dark and the first portion is in dotted. Okay, but when you see in the clock cycle 5, okay, the first portion is in dark and the second portion is dotted. Okay, so what it actually means is, the register read will take place at the right part. Okay, and the register write will be taken place at the first part. Okay, so this is how we have divided the two parts in the register to show register read and write happening at the same clock cycle, but also there is no conflict. Okay, so during the clock cycle 5, when you see the instruction 1, okay, so the register write will be taken place at the separate core, that is the first part as mentioned in the diagram. And when you see the instruction 4, I4, okay, the second part, that is the register read will takes place, the first part, the decode only will takes place. So during the decode part, okay, so the register will be free, so that is the time we are allotting for register read, right? So this is how we can resolve the issue, okay, resource conflict of registers, of register read and write happening at the same clock cycle, right? Got it? Okay, so this is how we can solve the issue. Okay, so there is no conflict occurs during the clock cycle 5. Okay, so till now we have seen about the structural hazard, and the resource conflict occurs due to the memory and the registers, and we have seen how to resolve the issue. Now we will go for the data hazard. As I told you, the data hazard, sometimes we can't provide the data for the further instruction at the correct time, that leads to hazard. How to resolve that issue? See, for example, in the instruction I1, okay, so that is R1, R2 are the two registers as an input we are going to use, and we are going to store the result into R3. Okay, so that is how we are going to do it. And when you see the instruction 2, here we are going to use two registers, that is R3 and R4. Okay, so when you see here, we are going to give an input R3 and R4 at the clock cycle 4 for the second instruction, but we are going to get the result of the first instruction of R3 at only at the clock cycle CC5, right? So that leads to an hazard. Okay, so the writing of the result of R3 only at the clock cycle 5. Okay, but we are going to fetch the operand R3 at the clock cycle 3 itself for the second instruction. That leads to an hazard, because when the series of instruction to be executed, okay, so once the first instruction R1 and R2 result, storing it into R3, okay, so that result only have to be used for instruction 2, right? So this leads to the hazard. We can't provide the correct output of R1 plus R2, okay, unupdated information into the second instruction. That leads to an hazard. Okay, how we are going to solve it? Okay, so register read R3 will be taken place. So we will go for register renaming. Okay, register renaming for that particular thing to solve the issue. Okay, so that is one of the part, and try to do the instruction R3 plus R4 at the clock cycle 4. That also the conflict occurs, because we are getting only the result in clock cycle 5. Okay, so here also we can't read at the clock cycle 4. Okay, so now we are again renaming it as R8 plus R4 and try it. Okay, and the next is when we go for at clock cycle 5. Okay, so the in section R3 plus R4, if we try here, okay, so this is the time if it comes, okay, so that time the conflict will not occur. Okay, so if it is coming at the intersection 2, we have renamed as R6. When it comes at intersection 3, we have named it as R8. Okay, and when we come it at as intersection 4, okay, so that is the time, okay, we will check for whether any data conflict occurs. Here we can provide, because the first portion of the clock cycle 5 for the first intersection 1, okay, we will write R3. Okay, and we can provide very clearly, okay, we can provide very clearly at the intersection 4 the second core, that is the register read R3 going to happen. Okay, so this is how we can resolve the conflicts. Okay, so we are just, in the diagram you can see write happens for the intersection 1, that is at the first part, and read R3. Okay, so now we will get that updated result of R3. So we can solve the conflict of data, okay, output of R3, we can resolve it very clearly, right? So till now we have to provide bubble, okay, because we got an updated information of R3 only at the clock cycle 5, right? So until that time we should not do any useful information, that is we have to we can't proceed, okay, until the instruction at clock cycle 5, right? So when you see here, okay, so when you see this diagram, okay, so every time we have to see the first part is a decoding part, and the second part is register read, okay, occurs. Okay, so this is how we will check the conflict, whether any updated information occurs or not. Whenever the data dependence occurs, we have to solve the issue only by seeing it whether any data dependence occurs or not. Okay, so now when we go for the control hazard, okay, control hazard, how we can resolve the issues. Okay, so here we can see when the branch instruction occurs, we will check the branch instruction whether the branch to be taken or not. Okay, so here there is a problem occurs. So in the normal hazards, okay, normal sequential instruction to be fetched in a pipelining, the program counter value will be incremented by 4. That means the next instruction to get executed. But here if the branch instruction occurs, we are seeing that the processor have to go and fetch the 100th location. So automatically the program counter value have to be incremented by 100. Okay, so that is the time the hazard occurs, because the clock cycle 2, the second instruction will be fetched and try to execute, but we will get only during the execution time the branch instruction occurs, and we have to change the program counter value by 100, right? So that is how the conflict occurs. That is called the control hazard. The control hazard mainly occurs whenever the branch instruction occurs. During the execution time only we will know, and but we will try for decode in the next instruction, right? So when the control hazard occurs, okay, so here you can see, okay, so at the decode and the register read at the clock cycle 2, that is the time only we will know it is the branch instruction, okay. But initially the program counter value will be incremented by 4, okay, but here now only we will know we have to increment by 100 because the branch instruction occurs, okay. So initially the second instruction will be fetched as it is in pipelining, okay, not knowing that it is a branch instruction, okay. Once the first instruction get fetched, we will fetch the second instruction, try to execute the second instruction, but the processor have to go to the location 100 because it is a branch instruction, but we will get only at the end of the clock cycle 2, right? So now we should not do fetch the fetched instruction, okay, as it is, that should not be executed. So what we have to do is we have to store the result, okay, so the value of a program counter which is incremented by 4, but we have to go for program counter value which is to be incremented by 100 as it is a branch instruction. We should not execute the second instruction, okay. So what we have to do is we are going to use, okay, so when you use a technique here, for each branch install, okay, introduce a stall cycle, okay. So that is an branch is not taken and start fetching the next instruction. The branch is taken, need hardware, okay. So there are two options. We have a conditional branch, means whether the branch to be taken or branch is not to be taken, okay. So we are left one particular instruction after the 5-stage pipelining get executed, okay. We are just stopping and we are going to decide whether to take branch or not to take, right? So there will be a delay slot occurs, okay. So we will see in the coming slide how we can resolve the delay slot, but before that you should know, okay, the second instruction which is try to, it is fetched and try to execute, okay. So that we have to stop. So that's why we need a software, that is very important, okay. So if the predict is wrong, when you see the slide, if the prediction is wrong, cancel the effect of the wrong path instruction, okay. So we have to cancel it and fetch the next instruction. So branch delay slot have to be done and execute it anyway. If the instruction turns out to be on the correct path, useful work was done. If the instruction turns out to be the wrong path, hopefully program state is not lost, okay. So we have to stop. If the branch instruction occurs, we will stop it and we will have a time whether the branch instruction to be taken or not taken. That is the biggest challenge, right? So if it is not taken, then the normal flow we need, okay. So that's why we should not delete the original flow of the instruction. So we have to copy the instruction, that is the program counter which is incremented by 4, having that information have to be stored it into the particular location and we should not delete it, okay. So if the prediction is not taken, okay, so that is the time we have to use the normal flow, okay. If the branch prediction, that is a branch to be taken, then we have to go for the new set of instructions to be executed, okay. So this is how the software take part in a very important role, whether to branch to be taken or not taken according to the execution of the branch instruction, right? So how to resolve the branch delay slot? So during the branch delay slot, okay, so whenever the branch instruction to be taken or not taken, the delay slot occurs, we have to make a bubble. In order to resolve the delay slot, that is the time we can give provision, okay. So when we do some useful information during the delay slot, that is the time also we have to check, okay. So when you see in this particular slide, okay, so from the first diagram you can see, okay, the delay slot occurs after the branch instruction, whether the branch to be taken or not. That is the time. The previous instruction, when you see, it is data, it is not a data dependence, okay, because we are not going to store the result into R2. When you see that the add R1 comma R2 comma R3, okay, and when you see if R2 equal to 0, okay, so when you see if R2 equal to 0, then the delay slot, okay. So here when you see here, R2 is used as an only input, okay, for the add instruction. Okay, so that instruction can be put after the branch instruction. So it is not data dependence, we can rearrange the thing. Okay, when you see the second condition, that if r1 equal to 0, then the delay slot occurs. Okay, so that is the time it will check some the previous instruction whether we can rearrange or not. We can't use d add r1 because it is a, we have to we can't rearrange it, because after doing dad r1 comma r2 comma r3, then only we can go for checking the condition, right? So but we can see the previous instruction, that is d sub r4 comma r5 comma r6, so it is not a data dependence, so that particular instruction can be put after the branch instruction. Got my point? So this is how we can resolve the issue. When you see the third thing also, you can see if r1 equal to 0, then okay, so then it will if the branch instruction occurs, it will see the previous thing. So here also data dependence occurs. Okay, so that is the result have to be put it r1, so we can't rearrange it. So here also we have to we can see the next instruction, that is or. Okay, that is r7 r8 r9, that is not dependence with the r1 equal to 0, so we can follow the instruction, right? So this is how we have to solve the issue of delay slot. So in order to improve the performance, we can rearrange the instruction which is not data dependence. Okay, so thanks for watching. Till now we have seen about the pipelining. We are improving the performance. So for that we are going for three types of hazard: structural hazard, data hazard, and control hazard, and we have seen how we can resolve the issue. Thanks for watching.